Okay, so um, again, it's a pleasure to be here virtually to give this talk. So before I begin, I remember giving a talk at giving a talk at Tsinghua roughly 10 years ago. And as you can tell from this photo, many things have changed. I have certainly gotten much older and probably gained a lot of weight. And over the past 10 years, I have been working on a number of different projects. But one thing that has pervaded through all of my projects is that humans are always an integral part of my projects. So to borrow the famous words from Abraham Lincoln, I titled my talk today, Intelligent Systems of the People, by the People, for the People. So I want to start with an overview slides of some of my recent projects on this, I guess it's a form factor graph from the millimeter scale all the way to the kilometer scale. So to the very left, we have a project. I'm calling this time delay ASIC. So this is a project where we created a custom integrated circuit that can compute the time delay between multiple channels of microphone. And to the very right, we have a project where we try to compute the energy consumption of every single person in the city using available data sets that we can find. So, and I have color-coded these projects. Some of them are projects of the people, and some of them have humans as integral part of the system, and some of them have humans as the end consumers. So the first set of projects that I want to talk about is a wearable system that combines signal processing and machine learning to improve the safety of pedestrians and construction workers. And building on top of that, we created a generalized acoustic filter that can allow third-party developers to enhance any sound that they specify, as well as remove any sounds that they want to consider as noise. So that was a paper that we recently presented at IPSN 2022. Next, I will talk about a set of projects focused on jointly optimizing between energy consumption, occupant comfort, and air quality in commercial buildings. And we're able to achieve this using a combination of digital twins, a simulator environment, and a reinforcement learning-based recommender system. So these set of projects represents humans in the loop. And finally, I want to talk about a recent project where we are trying to provide fever screening of populations and using inexpensive sensors. So essentially, we are trying to be able to provide the accuracy of something that you see at airports, right? Those are usually quite expensive for $20,000 or $30,000 each. We're trying to achieve the same accuracy with something that's in the order of hundreds of dollars. And we're able to do that through a combination of machine learning as well as signal processing. All right, so let me dive into the first set of project. So this is pedestrian safety. I think this is something that we are seeing all over the world, right? We are paying more attention to the smartphones at hand instead of paying attention to the road. And as a result, people are getting killed or injured because they are not paying attention. So this project is trying to find a way to alert pedestrians when there is a vehicle that is about to hit you, right? So in this photo here, my student is holding a smartphone. He is wearing our wearable system. So this is the headset. And when there are vehicles that are on an intercept course, our system will alert the user so that he can avoid getting hit by the vehicle. So the first thing we asked ourselves is, what is the sensor we should be using, right? We could consider things like cameras or even LiDAR. But we ended up with using simple microphone array. And the reason is that even though camera and LiDAR provides much more richer amount of information, they suffer from problems such as they require line of sight, and they're also much more power hungry. So for us, we need to be able to sense vehicles that are potentially behind other vehicles, and we need this to work for many hours on a set of coin cell batteries. So we decided to go with acoustics, with simple microphone arrays. So the first thing we did is it even possible to detect the presence of vehicles using purely sound? And the graph here is showing on the top when a car is passing the user. So the car is honking at this point, and we cannot rely on this signal because not every car will honk. And as the car is passing the user, there is this air displacement noise. So that is very significant. Significant. But it is too late. We have to detect the vehicle well before this. So what we are really trying to detect is the noise, the frictional noise between the tires and gravel, as well as this tiny amount of engine noise. So as you can imagine, this is very challenging because in a busy urban environment, it's very difficult to hear these kind of sounds for a vehicle that's 60 meters away. So the next step we did is, well, what are the features that we should be using? There is something called MFCC. This is used widely in the speech community. So we played with this feature. It turns out that MFCC is not very good at distinguishing between vehicle sounds and regular urban noises. So the first thing we did is to construct our own feature vector, which emphasized different parts of the spectrum, the acoustic spectrum. And using this set of features, we're able to separate cars with background noises. So the next thing we did is, in addition to detecting vehicles, we have to localize vehicles. We have to know from which direction it is coming from. And for this, we need to use multiple microphones and rely on the time difference of arrival. So the features here we used include relative delay, relative power, and zero crossing rates. And this figure to the left is simply showing, yes, it is possible to localize vehicles using multiple microphones. So next, we have to design the actual embedded system. We want this whole thing to fit inside a regular headset. So what we did is, so we have to first ask the question, can we simply transmit raw audio signal directly to the smartphone and rely on the smartphone to compute where the car is and detect vehicle? And the answer is no, because acoustic or sounds are very bandwidth hungry, and it's not possible to transmit 4 channels of audio through either Wi-Fi or Bluetooth. So what we did instead is to use a microcontroller that's embedded in the headset to extract these multi-channel features, and namely the relative delay between the different channels, and use a Bluetooth low energy interface to transmit those features to the smartphone. The smartphone does have 1 channel of raw audio. So this is the microphone that you would normally wear when you are using a hands-free set. Okay, so this is a single channel that you can perform various types of acoustic feature extraction. And on the smartphone, it will perform detection of vehicles as well as localization. And finally, it will alert the user if a vehicle is detected. So this figure here is showing the circuit board that we built that fits into one side of the headset. What you can also notice here is that we're using 2 AA batteries. And sort of keep in mind that this is quite heavy, right? And the reason for that is we still need to consume a lot of energy to compute the relative delays. That's a very expensive operation. So what I want to show here is that another requirement of the system is real timeliness, right? The latency has to be small. So we have to really manage the various threads so that we can operate using this pipeline approach. So on top, you have the ADC that's continually acquiring new data. The feature calculations as well as the transmission to the smartphone has to all fit inside one time window so that this pipeline can run in a continuous fashion. And once we constructed our prototype, we evaluate this under 3 different environments: a campus environment, a highway environment, and a metropolitan area. So metropolitan is in New York, and campus is in one of the suburban campuses. The different color bars here is showing, the blue is showing the ground truth. So we have one student who is standing at the street, essentially looking at when vehicles are passing. We have the pause student. So this is pause is the name of the project. So this is a student who is wearing our device and he is listening to music and he is writing down. So we're counting how many vehicles that our system is able to detect. And we also have I guess a background, sort of a comparison student. We're calling this a distracted student. So he is listening to the same music at the same volume, but without the benefit of our system. And he's writing down how many vehicles that he detected. And what you can see in this graph is that our system is able to detect almost 100% of all the vehicles, while the distracted user can only detect around 64 to up to 80%. So our system, in fact, is able to, basically alert the person when there are vehicles coming. And the other graph that we want to show is the localization accuracy. So the blue bar is direction, and we're dividing the directions into 8 quadrants. And as you can see from this figure, it is fairly easy to get a good accuracy for direction. But for distance, it is much more difficult. And it's sort of, it's understandable because you have different vehicles that might be at the same distance from the user, but they could exhibit vastly different amount of sound. So you could have a truck that's much louder than a sedan, right? So simply using the power of the sound is not a very good way to measure distance. So one thing I hinted earlier is that we are still using a lot of power to compute the relative delay. And to address this problem, we created a custom integrated circuit that is able to perform multi-channel audio delay extraction at a fraction of the power consumption. And I'll talk about this next. So what is time delay estimation? You essentially have 2 signals, M1 and M2, and they are offset from each other by some delay D. And what we want to compute is essentially the convolution of the 2 signals so that you have a peak that occurs where the 2 signals overlap, right? So the delay here, the delta T, where the peak occurs, is what we need to find. However, using standard cross-correlation methods, it is very computationally expensive. So for a few milliseconds of audio, it takes millions of multiplications and additions. So fortunately, we found a paper that was published recently that says instead of computing the full cross-correlation between the 2 signals, you can take the sign of the signals and perform essentially a convolution of the signs of the signals. What you will get is something that looks very different from the full cross-correlation, but the peak occurs at the same point. And that's exactly what we need. We don't care what the shape looks like. All we care about is finding this delta T. So utilizing this knowledge, we constructed we designed a chip. We send this design to TSMC, and after half a year, we were able to get the chip back, and it consumes about 80 nanowatts in active state. So as you know, for a microcontroller, usually it's consuming tens of milliamps in the active state. So this is a significant power saving. So once we validated that this chip is working, we have to integrate this back into the overall system. And this is not trivial because we have to remove the microcontroller altogether. And once we remove the microcontroller, we are not able to get some of the previous features. So we have to redo a lot of the algorithms to make this work. But at the end of the day, we were able to create a version that runs using the ASIC. And we did the same types of evaluations and found that the accuracies are roughly comparable to the microcontroller version. But one thing that's very different is the power consumption. So this table here is highlighting the overall system power consumption between the two different versions. So in idle state, we were able to drop from 16 milliamp to about 12 milliamps. And in active state, it dropped from about 70 milliamps to 20 milliamps. So that's a significant improvement. The second metric that was quite important for us is latency. So using the microcontroller version, there was a long tail, right? Because executing the software code in a general purpose pipeline have a lot of unpredictable, a lot of sort of things that you cannot predict. So sometimes where we see a long tail of around 300 milliseconds, whereas using the ASIC, we are able to control timing much better, and we can control this to be within 100 milliseconds. So this is much better in terms of providing real timeliness. So once we finished the system for pedestrian safety, we naturally ask the follow-up question of what can we do with this system? Can we use it for something else? And it turns out the answer is absolutely. What about construction worker safety? At least in New York, almost every street corner, there are construction sites. And construction workers are getting killed or injured because they are operating these very loud instruments and they are not able to hear the sounds from vehicles. So it is a significant problem. So we basically decided, hey, what if we simply take the previous system and put this on construction workers? It turns out it was a complete failure. It just does not work. And the reason is that in a construction site, the noise is much greater than the signal. So imagining the jackhammers, right? These very loud construction equipments, they overpower the signal that we are trying to detect very easily. So we're facing a significant challenge here, which is how can we still be able to detect the tiny signals coming from vehicles from 50 meters away in the presence of loud noise. And for that, we decided to perform acoustic filtering first. We essentially want to remove the noise before we send the data into the classifiers. And so we did a little bit of research and see what is available in the field. There are essentially two approaches to this problem. One is multi-channel based spatial separation. And these include adaptive filtering and beamforming. The second class is single channel based content based separation. So things like dictionary learning and neural networks. However, both approaches have their shortcomings. So for spatial-based separation, you need prior knowledge of locations of the sources, and it's very difficult to distinguish multiple sources from the same direction. And for content-based separation, you need prior knowledge of the different sound sources, and it is very difficult to account for all possible sounds in an urban environment. So what we proposed is something that we're calling noise adaptive filtering architecture. And it is leveraging both spatial and content-based separation in a feedback architecture. And we're utilizing a library of noise models. And essentially, we're taking advantage of the fact that we have prior knowledge of construction tool sounds. And we also allow workers to supply their own personalized recordings if they choose. So this is optional, but they have this option. So let me walk through this architecture first. So what we start with is we have multiple channels of audio. So these are these 4 microphones that's mounted on the helmet of a construction worker. We apply a set of these filters. So initially, this is random values, but we will come back to this in the feedback loop. We first do localization. So we figure out what are the top N sources of sound. Next, we perform spatial source separation. So we separate that into, let's say, 3 different sound channels or sound sources. So next, for each of the separated sound sources, we try to detect if there is the presence of a noise that exists in our library of noise models. And here we are representing the noises as a mixture of Gaussians. And essentially, we're trying to say, is the observation falling into one of the corresponding template? And if so, we would use this template to update the bank of filters to essentially remove that particular sound. So this is where the feedback loop comes from. We are constantly updating this bank of filters based on the noises that we are able to detect in the sound. So once we have some idea of how to do the filtering, we have to construct the actual embedded system. And this is very similar to before. We have the front end hardware. It's now using a Cortex M4 microcontroller, performing standard FFT feature extraction, sending the features through BLE to the smartphone. But instead of sending those directly to the classifiers, we first perform noise filtering. So this is removing the loud construction tool sounds, the jackhammers, the cranes, or whatever that's present in the environment. And similar to before, we have to be very careful with the pipelining. We have to make sure that everything can run in real time. So to evaluate our filter, we compare this to a couple of different implementations of acoustic filter based on deep neural network, based on dictionary learning, and based on adaptive spatial filtering. And as one can imagine, our system obviously is performing the best. We are able to detect all of the vehicles, whereas all the other approaches missed some number of vehicles. So at this point, we have something that can work not only for pedestrians, but also for construction workers. So we have to ask the next question, what's next, right? It turns out there are so many different applications that can benefit from a filter that can enhance a custom specified sound and remove noises specified by the user. So we talked about construction safety, we talked about urban safety. We can imagine a wildlife scenario where we are trying to amplify the sounds of wild animals while trying to suppress noises from the environment, the wind, the rain, right? So in this case, the signal to amplify would be lions or elephants, and the noise would be environmental noises. We can think of a completely different example. Let's say in sleep monitoring, we are trying to monitor how well a person sleeps by looking at the snoring sounds. But we want to preserve privacy, and we want to remove any sleep talking. So in this case, the signal to enhance would be the snoring sounds, whereas the noise is the speech. So a flexible filter that can allow a third-party developer to specify what is the signal, what is the noise, is very powerful. And this is exactly what we try to tackle next. So the challenge here is that it needs to be able to filter enhance a wide range of sounds. It also needs to be adaptable to a wide range of sound models and features. So this is saying that not everyone is going to use random forest for the sound classifier, or use SVM, or use whatever the sound model is. And people may use different features. It may be MFCC, it might be MBIP, it could be simple FFT. So our system has to allow the flexibility of using custom features. And finally, it needs to be flexible to a wide range of systems. Could be different numbers of microphones, could be different types of acoustics. It doesn't have to be sound, it could be vibration, right? So what we were able to create is something we're calling AvA. It's selective noise filtering and signal enhancement. And the high-level idea for AvA is we are combining beamforming, which is physics-based, with data. So we're calling this content-informed beamforming. So this is combining something that is purely based on the physics of sound waves, together with sound models of various type of sounds, whether it's something to be enhanced or something to be removed. So I want to first describe this formulation. So this is formulated as an optimization problem. So we are starting with the standard formulation for beamforming. We are trying to minimize a loss function L. We are trying to find the coefficients W applied to a sound signal X, such that the sounds from directions represented by D are maximized, whereas all the other directions are minimized. So this is the standard formulation for beamforming. What we do is we add two data-driven constraints to this formulation. We say that the first part is the probability of the features of the output sound for the target sounds that we want to enhance should be greater than some threshold A sub E. And the probability of the features of the sound for noises that we want to filter out should be less than some threshold B sub F, right? So conceptually, it's a very simple setup. But what we need to do is to be able to solve that optimization problem. So to explain this, I'm going to sort of go through this. So essentially, we're trying to compute the gradients with respect to the filter coefficients W. And what we can see here is it's somewhat similar to neural networks, where you have a forward pass with different layers, right? And then you have a backward pass where you're trying to compute the gradient. Except that instead of the different layers, we are processing the audio through different stages. So starting off with the original sampled window, this is the original audio X of T. And we apply the coefficients, the filter coefficients W at this stage. And this is what we are trying to optimize, right? The W here. So after we apply the coefficients, we have the filter signal Z. And that goes through the feature computation. So this is where the developers can specify what the features that they want for their own application, whether it's FFT, whether it's MBIP, whether it's MFCC, it's whatever the developer specifies. So at this point, we have f of z. Then it goes through the actual the model where we try to classify sounds to be either one type or another, right? So this is, again, something that the application developer has to specify. It could be SCVM, could be neural networks, it could be random forest, it could be whatever it is. So at this point, we have the P of f of z. Then we have to go through the backward pass. So first, we try to compute a derivative of the classifier P with respect to the features. So we call this model adaptation. Then we compute the features with the derivative of the features with respect to the filtered signal Z. And we call this feature adaptation. And finally, the filtered signal Z with respect to the filter coefficients W. And we're calling this signal adaptation. By using the chain rule, we're able to simply multiply all of these together to form the full gradient. And of course, one requirement is that at each of the stage, they have to be differentiable. And it turns out most of the features and classifiers can be transformed into something that's differentiable. So my student is able to work out the math, luckily. So by applying this custom filter, we can enable a vast amount of applications. So we're evaluating our system using various types of sounds to enhance and noise to filter. So in this case here, the sound we're trying to enhance is the crying sound of babies, whereas the noise to remove are construction sounds. The table here is showing in the two different rows are the two features that we evaluated. One is using MFCC, one is using MBIP. So MBIP is the features that we came up with earlier for the construction safety project. We're also comparing three different classifiers: SVM with the radial basis function, random forest, and Gaussian mixture model. So for this particular application, the best performing feature and classifier happens to be MFCC and random forest for the signals and for the noises to suppress. This is the Gaussian mixture model combined with MFCC. For a different application, let's say we're trying to enhance the sound of dog barking and trying to remove vehicles. In this case, it is MBIP combined with SVM. And for entire different application, let's say we want to enhance the sound of piano and filter out speech. Here, it is a Gaussian mixed model combined with MFCC. So this is simply showing how flexible this generalized filter can be applied to diverse applications. So at this point, I want to switch gears and talk about a set of projects that have users as integral part of the system. So the project that I want to talk about is building co-optimization with occupants in the loop. So in the field, we actually have seen quite a number of projects that are trying to optimize building energy. So optimize HVAC settings to reduce energy consumption. But most of those research projects do not consider occupants as something that can be changed. So let me give you one example. If I have a person who is sitting in a large auditorium, those approach to optimization would still sort of spend a lot of energy to keep that auditorium warm or cool just for that single person. So what we are doing very differently is that we are asking the human occupants to take actions that can also help the building to optimize. So let me sort of describe in more detail here. The figure I'm showing here is simply showing that this is a wearable, this is a smartwatch app where it's showing the user the real-time energy footprint of the person, as well as a recommendation that can if the person takes this recommendation, he can save this amount of energy. So the intuition here is that, as I described earlier, if I can ask the person that's occupying a space to move to be in the same location as someone else, we can tune down the level of service to the original space. And that allows us to save quite a bit of power. So this is sort of, it's a form of spatial shifting. Another case is, let's say different students come to school at different times. If we can ask students to shift their schedule by a little bit, so that the earlier student arrives a bit later and the later student sort of arrive a bit earlier, we can also save a lot of power because the building can essentially not power on until the first person arrives. So this is sort of spatial shifting. So to enable these types of recommendations, we need to construct a recommender system. And to do that, we first need to monitor everything, right? We need to monitor the energy consumption of the building. We need to also know where people are. So this is the localization part. We have to construct a simulation environment so that we can simulate what happens when we move one person to another space. So once we have the simulator, we can then construct the recommender system that can use the simulator to figure out, what is the reward when someone takes a particular action. So once this recommender system is operating, it can send recommendations through smartphones, smartwatches, or regular web-based interface. And the rejection or the acceptance from the user becomes feedback that helps us to improve the recommendation so that we can push you recommendations that are more likely to be accepted. So here I'm just showing some of the interfaces. So to the left, we have a smartphone interface showing this person, if you move to this space, you can help the building save 1.2 kilowatt hour of energy. To the right, we have a smartwatch app, right? Move to lab space A, you can help save 1.5 kilowatt hour of energy or 1.2 pounds of burned coal. Right? So some of the previous research says it's better to give these numbers in something that's more I guess, relevant to the person's interest. So unfortunately, we're not able to actually change these HVAC settings in our building because the building manager is afraid that we're going to burn down the building. So we have to perform the evaluation in simulation. And what we can see here is that our system is able to save on average between 20 to 30% as compared to the type of systems that do not ask the person the occupants to take actions. So then we realized that people are inherently lazy. And if you ask them to take an action, if you ask someone to move from here to there, chances are they are not going to do it, right? Because we're just lazy. So instead of simply optimizing for energy consumption, we have to add something else. And here we are adding two additional things. One is comfort, and the other is air quality. So here we are trying to jointly optimize for energy consumption, user comfort, and air quality. And to do that, we have to add a couple of additional sensing infrastructure. One is comfort estimation. We are using these infrared cameras to estimate the temperature of each person's skin as a proxy. And I will talk about this project later on in the fever screening part. We're also doing air quality monitoring. So we deploy these air quality sensors throughout the building. And we, of course, have to construct a digital twin that can essentially reflect where people are, what are the different states of everything, and a simulation environment as usual. So here we are training a multitask learner using our simulation environment and using our digital twin. The key here is that the building manager can specify what I'm trying to optimize for, right? So let's say right now it's COVID-19 pandemic, and we need to make sure the air quality is good. So I can say, let's optimize more for the air quality and perhaps sacrificing energy. In a different time, I can say, it's more important to me to make sure everybody's comfortable and productive. And I can simply change a coefficient here and be able to optimize for comfort. And we can use this multitask learner to train a recommender system that can then provide recommendations to individual occupants that can, with actions that can optimize for whatever is being that we are trying to optimize for. Right? So it's very flexible. All right, so at this point, I will quickly switch to the third set of projects. This is the low-cost continuous fever screening project. The motivation here is that essentially we have two different things that we're seeing, right? One is you have these forehead scanners that when you go to a restaurant, when you go to a business, you put your forehead in front of it for a few seconds. So this approach is, it's very slow, right? You have to stop there for some time. So it disrupts the flow of traffic, and it's not scalable for applications where you have large traffic flow. You have this other set of approach where you have, so in airports, you often see a monitor that looks at people when they walk through this monitor area in a line. So these systems are much more expensive, on order of thousands or tens of thousands of dollars. It turns out they are still not very accurate, right? So what we hope to achieve in this project is to use low-cost hardware combined with calibration, machine learning, and signal processing to enable continuous fever screening of populations. So we do not want people to stop and wait. They can go about their business as usual, and we are still able to monitor to see if anyone has fever. So to achieve this, we took a couple of different, we developed a couple of different techniques. So one of them is distance calibration. So we have to calibrate for how far away the human subject is from the thermal imager. We're using bounding boxes, and we're using the parallax effect because we have multiple, we have a RGB camera and we have a thermal camera. We're also calibrating for the surface, in this case, the human skin, as well as the medium. So we calibrate for the air, temperature, and the humidity of the air. But most importantly, we are doing something, we're taking advantage of the fact that when people are moving through the observation window, we are not asking them to stop, right? They are moving through this window randomly. So we are essentially able to capture multiple frames of this person's head at different times. And here we are creating a 3D point cloud model for every unique person's head. And we're effectively pasting each frame of this person onto this 3D model head. So we're able to take multiple frames and be able to improve the data set that way. And also we're doing model mapping to these particular thermal points. So the temperature at the forehead, at the temples, at the cheek, they're actually different even for the same person. So we calibrate for these thermal points. So with this approach, we're able to improve the accuracy significantly. So from a systems point of view, we constructed with a front end or edge device using the FLIR 1 Pro camera connected to a JSON Nano. It's doing some simple image processing. The data is transmitted to a backend server where we used Redis in-memory database. We use a couple of different data processing. That's essentially what I described earlier. And then there is a client that can connect to our server. We're using these Docker containers so that we can essentially have multiple clients on the same server. And we deployed the system at Columbia Doctors Midtown. It is essentially a hospital with hundreds of patients per day. And we were able to screen over 4,000 real patients over 10 months. And the accuracy here is essentially within 2.5 meters, we have average accuracy of around 0.4 Fahrenheit. And at 3.5 meters, we have something about 0.6 Fahrenheit. So this is much better than any of the commercial fever screening devices that people can purchase for even tens of thousands of dollars. So before I conclude, I want to talk about one more thing. This is a recent sensor hub project. We're calling this a sensor hub project. And the reason for this project is we are collaborating with a couple of different other collaborators. Some of them are from civil engineering, from mechanical engineering. And it turns out we are constantly reinventing the same thing, right? So the key idea of this project is, can we create some sort of a modular sensing platform that can make it much easier for non-scientists to deploy sensing applications? And we decided to go with Raspberry Pi because everybody knows how to use Raspberry Pi. We developed a carrier board that is able to allow you to essentially plug in, mix and match different sensor modules to stick on top of this carrier board. And we are trying to build a large library of sensor modules that can have different sensors attached to it. And the key here is that it is able to configure itself without any sort of expert knowledge. So I guess I'll skip some of these details and just show this here. So we have essentially a dashboard that's running on the Raspberry Pi. If the user plug in a particular sensor module, the dashboard will automatically detect what sensor module it is and download the appropriate driver and configure it. So you do not need any kind of expert knowledge to be able to configure this Raspberry Pi and put in 4 different kinds of sensor modules to make it work. And we use the EEPROM so that it encodes what type of sensor module it is. And the software that we have written on the Raspberry Pi will pull down the drivers automatically. And for those who are familiar with the Linux system, you can interact with the sensors directly or the sensor data directly. We created a pseudo file system so that the sensor data appears as files. So if you know how to work with a file in a Linux environment, you are able to work with all of the sensors that we have. And so far, and this is really recent, so over the past 3 months or so, we created about 8 different types of sensor modules. Some of them for ambient environment, for ambient light, human activity, IMU, thermocouple, PM, auxiliary, I2C, indoor air quality, gas sensor, right? So the hope here is that we can create an ecosystem and a community that we can enable a vast number of applications and provide various types of sensor modules. So with that, I will conclude, and I want to thank all my students who did all the hard work, and I'm happy to take questions.